We can also work with the unequal segments. So the size of the segments can be not equal. In the previous examples and applications, we had equal size segments, but now we have unequal size segments. Then we can use the trapezoidal rule easily by simply applying it for each segment separately, then sum them all. That's very simple. And let's show an example about it. So let's say we have this unequally spaced data. You can see that from 0 to 0.12, then 0.22. So here the segment length is 0.12. Here say 0.1. Here 0.1 as well. Now here 0.4, 0.4, 0.4, 0.10, 0.10, 0.6, 0.10. So there are uneven data. For this, we simply use the trapezoidal rule at each integral, like here, here, like this. Then sum them all to get the integration. The tree value was this. When you use the trapezoidal rule at each segment, the error is 3.8%. This is pretty good actually, because we are using a kind of a composite trapezoidal rule with very much, so too many data. So it's getting closer to the true value. You can see on the right hand side the segments of this integration with trapezoidal rule, which gives a linear interpolation or linear approximation of the areas. We can also use here the Simpson's 1-3 rule, 3-8 rule and 1-3 rule. If you want to, you can do this because there are some segments which are equal. For example, this is just one segment, 0.12 length. But here 0.1, 0.1, these two segments are the same. So for these, you can use 1-3 rule because we have 3 data, only one single application of it. In the next 3, 4, 4, 0.04, 0.04, 0.04 distances. So 3 segments, which is suitable for 3 divided by 8 rule, because we have 4 points here. The next 2 has 10 and 10, 0.10, 0.10. segments, equal segments. So for these equal segments, you can also use another 1-3 rule. But for the last 2, this is 0.06 and 0.10 or 0.1 actually. Uneven, so use trapezoidal again, then sum them all. Let's check that in the following slide. But before that, we have some notes here. Yeah, adjacent segments are equal with some of them, we said. We can also use Simpson's rule for it. And this leads to more accurate results, and check example 21.7, which is in the next slide. In the previous slide, we said that we can use also the Simpson's rule for uneven data if we get some equally spaced data, 2 or 3 of them. And this is the same example. And let's check that. Let's recompute the integral for the data, but use Simpson's rule. And for that, we showed this already. For these 2, we have equal space, and these 3 we have equal segments as well, which is suitable for 3-8. This is suitable for 1-3, and these next 2 are suitable for 1-3 as well. And the first one and the last 2 are actually in different size of segments. That's why we need to use trapezoidal rule in these. So trapezoidal rule for the first segment for these 2, then Simpson's 1-3 rule for the next 2. For these 3, actually just one single application is enough here because we have 3 points. Then the next 3 segments are also equal, and 3-8 rule is suitable because we have 4 points with equally spaced data. Fine, in here we have 1-3 rule as well with equally spaced data of 3 points. It gives us this value. Then for the last 2 we have the trapezoidal rule again. Here one trapezoidal rule, here one trapezoidal rule. Get the values. You can make the calculations by yourself. I'm keeping that for you as an exercise. The area of these individual segments can be summed. So sum them all, the results, and the result is this. And you can see that we have a very good error, 2.2%. So this is very similar to trapezoidal rule, but it's a little bit better. In the use of trapezoidal rule separately for each segment, we actually calculated 2.8%. In here, we have 2.2%. This is better because we use in some of them a higher order integration. But we see that this didn't affect so much. So actually the effect of these depends on the function type and the order, it can change from a function to another function. The effect can change. So actually this is always better, but the effect can be lower or higher. Here it's a low effect compared to the single only trapezoidal rule application at each segment. You can check that from 21.7 example, and this is the example 21.8. So we can use an algorithm to be able to write a code for unequally spaced data. For the trapezoidal rule application, it's very simple. Just sum each segment, use the trapezoidal rule, then sum it with the previous one and get the final result by summing them all using this for loop actually. With the combination of Simpson's and trapezoidal rules, first we need to define the differences between the points of each segment if there are actually equal points. If it is 3, then you can use Simpson's 1, 3, and if equals 4, then you can use 3, 8. So this is actually like one entire algorithm. I had to divide it by 2 here because my page wasn't enough to fit them in one column. You can write this in MATLAB, for instance, to get this uneven function of application of Simpson's and trapezoidal rule. Here also the trapezoidal rule if k equals 1, etc. And these are useful to write in MATLAB actually.